All right. So let's start our second session for the tutorial. Okay, for today's afternoon, we invite the former deputy head of Geotechnical Engineering Office, engineer Philip Chong. Okay, hope you can raise up several questions to ask him because he has extensive experience in the design industry and also academic research in the university because he's also the adjunct professor in Hong Kong U. And so it will be very helpful for you. Okay, so today will be our last tutorial for the lecture 3. Okay, later in next week or in the following weeks, Dr. Wu will guide you about the lecture 4 and the lecture 5. Okay, mainly for the tutorial, actually we will have the tutorial for lecture 4. For lecture 5, we don't have any tutorial. Okay, and here I want to discuss with you and about one question raised up by one student. Okay, he asked me about that in this slide 39 for calculating the normal stress on the failure surface, the sigma n. Okay, it's calculated by the gamma saturate, the unit weight, the saturate unit weight. But in the slide 44, actually we use the effective unit weight here to calculate the sigma m prime. Okay, actually it's quite obvious. One is the sigma m prime and one is sigma m. Okay, you see the sigma m. But both of these actually is based on the effective stress approach. Effective stress approach. All right. So the meaning of effective stress approach is we need to consider the effect of the pore water pressure. Okay, we need to minus or deduct the pressure due to the pore water pressure, right? So here in slides 39, even though we use the gamma saturate, actually when we really calculate the tau f, we still use the sigma v prime. You see, total minus the pore water pressure is equal to the sigma v prime, right? Both of them actually is based on the effective stress approach. The only difference is when do we consider the effect of pore water pressure, right? So this is also, something I want to clarify, okay, more with you. And for this part 1, we still have one example left here. Okay, using the Philinus, Bishop, and Jambot method of slices, determine the factor of safety in terms of effective stress. Okay, for the sub-question A, using the peak strength parameter C prime and phi prime. And for sub-question B, use the critical state parameter phi CV prime equal to this value. Okay, and for the critical state, the C prime is equal to 0. Okay, we assume that for the critical state, C prime is equal to 0. We only have one phi parameter. The unit weight of the soil both above and below the water table is 20 kilonewton per square per cubic meter. We discussed already for the Jambot, for the Philinus and the Bishop method, right? This one, this one, this one, this one. We discussed already. And now let's move to the Jambot method. Okay, how to calculate these two. Okay, let's move to the Excel. Okay, I think you can see my Excel file now, right? I already shared it. You can see that as we discussed, all the value in blue color, okay, all the value in blue color is some value you cannot calculate or determine manually easily. Okay, so we will directly give to you this value. Okay, this value, blue one, will be all given to you. And for Jambot's method, the difference is here. For Jambot's method, there is a sec alpha square, but Bishop is only sec alpha. And the bottom item, W tangent alpha summation, is different with the W sine alpha summation for the Bishop method, right? So we know alpha already. The only thing different is how to calculate the top and bottom item, right? And then use the iteration method to get the final result for the factor of safety by Jambu method, right? So I will not go to detail about what is this, what are these parameters come from, okay? Uh, you can go through by yourself if you forget, and but the only difference is the equation, okay? Is the equation. Just to be careful about the calculation process. So after 3 times iteration, we get this result, okay? And as we said, the result from the Jambu's method will be not that accurate compared with the Bishop method, right? So that we need to use the correction method for simplified Jambu's method. You can see the F0. F0 is the correction factor. Okay, it's determined by the D and L. This is the D. This is L is the length. The length connecting the ending point, the most left-hand side point and the most right-hand side point. Okay, the length of this one and here is equal to 14 meter, and the D is okay at the middle point, the maximum, I should say, the maximum value between, or the distance between this connecting line to the failure surface. Okay, this is the maximum value, D, 2.3 meter. Okay, use 14 and 2.3, we get it into here. After correction, you will see that the F value, you see this one we just discussed from the Excel file. After correction, it will be enlarged, right, to this value. And this value is relatively similar to the result from Bishop. Okay, so this is correction based on the Jambu's method. You see, after, if we use effective stress parameter after correction, these two values is quite similar, right? Quite similar. So this is easy, right? D and L, we use this one, and the DLL, and we see this slide again for different conditions. This parameter will be different, right? This parameter will be different. So for C equal to 0, effective stress. For phi equal to 0, total stress approach. For C and phi larger than 0, it possibly is a critical state, critical parameter we will use, right? So for different condition, we have different correction equation to use, okay? All right, this is for the first part of lecture 3. We finish, and let's move to the second part of lecture 3. Okay, here we start with how to consider the earthquake load, right? How to consider earthquake load. We use the acceleration of this earthquake to divide it by the G, the gravity coefficient, okay? So we can get a ratio between the acceleration and the G, and then you utilize that ratio to multiply the weight, the original weight of that slice, okay? Then get this result as an external loading acting on the slice, okay? Acting on the slice, you see here, this one. We get this, due to the earthquake loading, we get an equivalent, or we can say that, equivalent external loading on top of this slice, okay? Then we get the decomposed force and decomposed force in the vertical and horizontal direction, okay, to apply as an external loading on the soil slice. Okay, this is how we consider the earthquake loading. And we discuss about the Jambu's method with the soil nail, okay, with the soil nail, right? The soil nail will be also decomposed in the horizontal direction and vertical direction, okay? This is also another type of external loading, right? External loading. So we should take this external loading into account in the equilibrium of force, okay, in the vertical direction, right? Because in the vertical direction is what we do for the Jambus method, first part. And the second part is resolved along the base T, tau, or the friction direction, this one, right? This one. So we, for this, along this direction and along the vertical direction, both of them we should consider about the contribution of the TSI. All right. And here, if we want to calculate the EL and the ER, the left-hand side force and the right-hand side force on this slice, we need to calculate one by one, starting from the slice one, okay? Because the EL of slice one will be equal to 0. We're starting from this one, okay? Then the EL start slice 2 will be equal to ER slice 1, okay? Then step by step, then we get the ELN, this one. And then the ERN again is equal to 0, okay? We discussed already. If we do the summation of EL and the ER, the final result will be equal to 0, okay? Because as I said, all the force, if we take this one, this slope as a complete body, okay? All the force here, EL or ER, are all internal force for this slope body, okay? So the internal force will be anti-balance with each other, right? Will be balanced with each other. So the external force here is equal to 0, external force here is equal to 0. That's why the internal force will be also equal to 0, because they are all anti-balance with each other, okay? Internal force, you see, internal force. So later, we also discussed about several important concepts in the GeoGuide number 7. Okay, you see here, this effective length is quite important, okay? Only this part will contribute to resist the soil slope from moving, okay? The effective length is very important. You will have one very similar definition of effective embedded length in the lecture 4, okay, as discussed by Dr. Wu. So they are very similar. And also we consider some different, okay, I can't erase it, okay, okay, no problem. We discuss some failure mode for the soil nail system, okay, like the overall stability, like the sliding or bearing, okay, due to the soil nail itself, or the bonding between the soil nail and the grouting, or even some structure failure, okay, structure failure. You see, we discussed already. And this one is important, how to determine the allowable tension capacity, okay? We have 3 different types, okay? We will compare the minimum allowable tension force to exert different failure, okay, type. Then to determine the smallest value from these 3, okay, which means that type of failure will happen earlier, okay, will happen earlier. So that we will say that smallest value will be regarded as the failure force, or we can say it is the allowable tension capacity of this soil nail. Okay, we have 3 different types. And for the second type, the FOS value is based on where the soil nail bonded in. Okay, if the soil nail is bonded in a weathered granite or even the volcanic rocks, okay, which means the bonded material is quite stiff, the quality is quite high. Okay, so that this factor of safety can be a little bit smaller, which is equal to 1.5. Okay, if the soil nail is bonded in a soil rather than the rock, the soil, the stiffness will be lower, the strength of the soil will be lower, right? So that we will have a higher factor of safety, which is equal to 2.0. Okay, so we can say that in order to design on the safe side, so for the soil nail bonded in the soil material, we need to use a higher factor of safety. You see, right? So uh, for this one, the first one is allowable tensile capacity due to the breakage of the reinforcement, right? We consider about the corrosion of the rust problem to -4 here for the original diameter, okay, to decrease the area of the reinforcement. The second part, we also discuss some real measured data, you see. And for the second part, the second type of failure is failure between soil and the cement grouting. This intersurface, right? This intersurface. And we consider the contribution of the cohesion and we consider contribution of vertical stress. Why? Because this looks very similar to the Mulholland failure criteria, right? One part is contributed by the cohesion, one part is still contributed by the friction. This mu star, we will take it as equal to tangent phi prime. The phi is the angle of shearing resistance of the soil under effective stress condition, okay? Which means this phi value actually is the phi of soil. Okay, even though we consider about the, we are considering the intersurface between grouting and the soil, but we use the phi soil as a friction angle between S and grouting, soil and grouting. Okay, we just do this simplification, okay, to use this one directly to represent the friction between soil and grouting. Okay, this is one simplification. And another one, we will convert the circle section into a plate section, as shown here, to consider the friction contribution by the soil and the grouting. You see, we have a 2 here because the force will applied on the top surface and also the bottom surface, so that we will have a 2 here, the sigma v prime, right? That's why we have 2 here. And another thing is we all use the effective length to calculate this L, okay? Because only this LE is effective to contribute the resistance to stabilizing the soil slope, okay? So that we will use effective length. And here we discuss in quite detail, okay? Will these two will be the same? Of course not, as I discussed with you just now, right? They will not be exactly the same. And the second one, the effective stress, vertical one, sigma v prime, will still be the same as the original vertical overburden pressure before drilling a hole? Of course not, because we also show some real measured data, right? After we drill a hole, actually the pressure decrease, obviously, right? Obviously. So that we will kept the vertical stress at 300 kPa. Okay, try to design on the safe side. So here actually, why do we discuss about this question is to help you to understand some mechanism behind. Okay, all the equation in the design code have some certain reason. Okay, based on certain assumption or based on some simplification, so that it means there must be some limitation for that equation in the design code. Okay, so as an engineer, we should know the background, why we have that equation there. Okay, what is the limitation of that equation? Okay, so that when we use it, we will know what caution should be made. Okay, regarding using this equation. Okay, so that we have some questions here and discuss with you the reason behind. We can do some tests. Okay, we build up a physical model test to consider this question as shown in that figure, right? And we can also do some interface sharing test to determine the phi soil to soil and the phi soil grouting, okay, will they be equal or not equal? Okay, we need to do some tests to verify this question. Okay, uh, as I said, this soil phi grouting, actually in the field, this value is very largely depend on the workmanship. Okay, workmanship. Sometimes we add the pressurized grouting, which will increase this value, of course, because some grouting will penetrate into the soil, which increase the interlocking or the bonding between the soil and the grouting, right? If the workmanship is poor, this value will be decreased, okay? Will be even lower than this value, okay? That's possible due to the workmanship. So here in the design code, we directly to use the phi SS prime, okay, as the coefficient. Okay, direct to use this one because it is more simple, okay? And we still have one example here. Let's directly to start the discussion about this example. For a soil nail stabilizer slope, the soil has effective cohesion 10, C prime is equal to 10, and the effective friction angle is 29 degrees for the soil, and the unit weight is 20 kilonewton per cubic meter. Soil nail rebar diameter is 40 millimeter. The rebar diameter is 40 millimeter, right? The rebar, so that we need to consider about the crust problem. And the yield stress is here, and the hole diameter is this value, 150 millimeter. The hole diameter means the hole for the grouting, okay? For the grouting, and we will have a rebar in the center. Horizontal spacing, 1.5 meter. Okay, I want to start with what is the horizontal spacing first. Okay, horizontal spacing, because all the equation and the discussion about the FOS calculation is based on a 2D condition. You see, we always draw this 2D figure, right? But in the real condition, the problem is no longer a 2D problem. It will be a 3D problem, right? So we normally to see from this direction, then we get the cross section, right? It's 2D. But in the question, we have a horizontal spacing equal to 1.5 meter. This 1.5 meter means this distance or this distance, okay? 1.5, 1.5, right? So which means the distance along the width along this direction of the slope or this direction of the slope, the distance between two consecutive soil nail is equal to 1.5 meter. Okay, this is the definition of horizontal spacing. So if when we calculate the force, for example, this one, of the soil nail, we get a force value. Then we need to divide the force value by 1.5 meter to get the so-called line load of the soil nail. Okay, the line load of the soil nail. Okay, to get the TSI. Okay, well, for all the TSI here is a line load concept. Okay, a line load, not a force actually. The unit of this TSI is always kilonewton per meter because we always consider about a 2D cross section. Okay, this drawing is only 2D, right? If we consider about the force, it will apply on a 3D condition as shown here. Okay, so that let's see the process how to solve this problem. The first one we need to calculate allowable soil nail loads. Okay, allowable soil nail loads. We know there are three different failure types of the soil nail. The first one is the breakage of the reinforcement. The yield stress multiplies the corrected area considering the effect of crust, right? Corrosion. Okay, let's see. It can be corrosion. Due to the corrosion, the D will become smaller, right? So the factor of safety is here. We get this final result. And for the SG, the soil granting, okay, as we discussed, it contributed by the cohesion and also contributed by the friction, right? So that we will have this equation and we consider about the LE here. LE is equal to 5 for both soil nail. And the FSG is equal to 2. No problem, right? FSG is equal to 2. So we get these two results directly. Okay, then let's see the third failure type is between the rebar and grouting. So the beta value is equal to 0.5. Okay, here, because it is the high yield rebar, okay, not plain rebar. Okay, for plain rebar, the beta will be equal to 0.3, okay, because the surface is relatively smoother, okay, compared with this condition. So here, beta is equal to 0.5. And we also consider the corrosion problem. We get this result for the TGR. You can see that the TGR value is much larger, okay, than this value. Okay, almost more than 20 times larger, right? Also, for the first design failure type, is also quite larger, much larger than the second failure type. Okay, so we can conclude that the second failure type will happen earlier. Okay, will happen earlier because this allowable tension force is determined by this STG. Okay, it mainly depends on this one. So we get this result, and we conclude that this one should be the smallest value, this one should be the smallest value, right? And as we discussed, we need to divide the force by 1.5 to get the line load. You see, the unit becomes kilonewton per meter, right? Kilonewton per meter. Then we can use these two value into what we discussed in the mathematical way, okay, using the Jambos method, Bishop method, or anyway, anything else, okay, because all of them are based on the 2D condition. So we get this two line load value. Okay, then let's move to the Excel file to consider when the soil nail install, how can we consider about the FOS? Okay, I think you can see my Excel here, right? With the soil nail condition. So if we install the soil nail in the slice 3 and the slice 5, okay, we should have new parameter called VIHI. Okay, this is the decomposed force of the soil nail along the vertical direction and horizontal direction, right? So for the third slice, we have one soil nail, and for the fifth slice, we have another soil nail. So the soil nail only apply or only take effect on these two slices, okay? No force on the remaining slice, you can see, right? Only these two. Because when we talk about the effect of soil nail, we will take out, for example, slice 5 out. We will take out this out, take this out to consider the soil nail force as an external loading, right? As an external loading. Then we calculate the equilibrium of force along the vertical direction and along the shear force direction, right? If you still remember. So that's why what I want to say is let me copy another figure to you to help you to be more clear, okay? Here, this one, you still remember, right? How can we consider this effect of soil nail? We will take this TSI into two decomposed force, VI and HI. So when TSI is only applied on this slice, okay? so that we only consider for slice 3 and slice 5. No need to consider the effect of soil nail for slice 1 to 2, for slice 4, for slice 6 to 8. Okay, no need to consider. So we only have these 4 for slice 3 and slice 5, right? And with the condition with soil nail, we should use different equations with the VI, PI, HI here. If we use Jambu's method, okay, we already discussed how to get this equation, so that we need to have a new some new parameters to calculate. This one, right, to determine the bottom item. You see bottom item here, we should have VI and HI and do the summation, right? And for the top item, we also need to have some new item here, this one, right? WVI minus UB tangent phi prime is this one, right? And finally, we can get the top item for the Jambu's method with the soil nail. Right? We calculate the summation for the top item. Okay, so the only difference is how to calculate the new item for the top part and the bottom item for the soil nail factor of safety calculation. Okay, nothing new. Okay, nothing difficult if you understand the procedure for calculating the FOS based on Frillenius and Bishop method. Okay, here we only apply the VI and HI, okay, here for the soil nail. Okay, and we also do the iteration, 3-time iteration to get the result, 1.894, okay? And for the calculation of the inter-slice force using Jambu method, as I said, I already list this one, okay? So the detail about the equation to calculate the inter-slice force. The EL for the slice 1 is equal to 0, right? And step by step, okay, one by one. From EL for slice 1, we calculate the ER for the slice 1 because we know this equation. Okay, we know this equation, and so that we can calculate for the ER1 and then the EL2. This is EL2, which is equal to ER1, right? And EL2 calculate the ER2. And for slice 3, okay, should be careful because on top of slice 3, we have the soil nail. We have VI and HI should be put here. Okay, should be put here because VI and HI are all the external loading. So we need to consider them in the equilibrium of horizontal force, right? So that we can get the ER for the slice 3. Okay, we only show the equation here for the first 3 slices, but the other result here for other slice, actually, we also put here in the Excel. You can go through by yourself, okay? It should be no problem, I guess. So, okay, that's all I want to share with you about the, let me see, about the condition with soil nail for the Jambu's method. Let's come back to the PowerPoint, okay? And for this example, okay, for this example, we get this result, Jambu's result, okay? Method 1.894. This is the minimum factor of safety, okay? And here also we discussed about this already, about the detail how to calculate, okay, from the first EL1, one by one, to get the inter-slice force for the first 3 slices, okay? The equation we based on is here, this one, okay? If we have the soil nail, we should have VI and HI, okay? If we don't have the vertical, the soil nail, actually no need to include these 2 items, okay? Only W sine alpha and the T, okay? So you see, we use this one, we use this one, right? This cosine alpha should be put at the bottom, okay? That's why we will have this equation. Okay, here, if we have the solenoid, we use this equation, okay? All right, so we finished the example of the solenoid condition. Okay, do you have any question about these two examples, with and without solenoid? One thing I want to discuss more is something different. Here, as I said, the solenoid force is only applied on the slide 3 and slide 5, right? And in your assignment, the acting point of the solenoid is at the interpoint of two slides. Okay, what do I mean? Is the acting point of the solenoid is just at this point. You see, at this point. Is the interpoint between slide 3 and slide 4. Okay, this is the solenoid acting here. Someone may ask me, if the solenoid, the acting point is at this point, so do we need to divide the solenoid force into two parts? One part is for the slide 3 and another part is for the slide 4. Okay, actually no need to do that, because even though the force applied on this point, actually the solenoid only contribute to hold the slide 4, because if we elongate the force along the solenoid direction, right? If we elongate along this direction, all the force actually only contribute to hold the slide 4 here. Okay, nothing to do with slide 3. You see that, right? So all the force of this solenoid, okay, can be regarded as the external force on the slide 4 only. Okay, nothing to do with slide 3. Okay, so this is a condition you will confront in the assignment. Okay, I want to discuss with you. Okay, so for the assignment, this is the only thing I want to remind you. And another thing is, I hope you can plot the figure. Okay, plot the figure carefully. Okay, for your assignment. When you submit your assignment, when you calculate, when you do your assignment. Okay, I hope you can draw the figure and present all the calculation process in a table format. All right, so this is two requirements for your assignment. And for this assignment, I think you can just refer to our very detailed Excel file, okay, then get the result, okay. One student asked me whether or not you can use Excel in the examination, okay. Of course, you cannot, okay, because in the examination, you are required to share your screen, okay. On your screen, the only thing can appear is the examination paper, okay? And another one is to monitor your examination environment, okay? So you still have to calculate manually or calculate using the calculator, okay? To list all the parameters in a table, okay? You cannot use Excel, okay? Because you are required to understand and master the process, okay, in a very familiar way, okay, to calculate. You just using the calculator, okay. If you use Excel, actually, the examination has no meaning, right? Has no meaning because everything can pump out easily because you have already set up all the equation in the Excel, okay. So this is okay. I respond to the student's question, and we also have one session for the instruction period. Maybe I will announce the time later. During that instruction period, we can discuss about the examination. We can discuss about anything else related to our study, related to this course, okay? I will announce this time period later. It will be at the middle or later part of April, okay? So hope you can attend if you have any question you want to ask, okay? And Okay, that's all for today's tutorial. Start from next week, and Dr. Wu will share with you about the tutorial for lecture 4. Okay, we have no tutorial for lecture 5. Okay, so we finished all the material for first 3 lectures until now. Okay, relatively speaking, the first 3 lectures, the content is more challenging. Okay, because we have a lot of information. Okay, so hope you can understand well. And if you have any question, you still can send me email. Okay, so this is what I want to share with you for today's tutorial. Do you have any questions? You can ask me now.